Good morning and welcome to this, the third lecture in the course of stochastic hydrology. In the previous class, we have introduced the concept of bivariate distributions, where we are interested in the simultaneous behavior of two random variables x and y, and we introduced the concept of joint probability mass function and the joint probability density function. And then we went on to see the distribution of one variable irrespective of the other variable, and we called it as marginal density function or marginal probability mass function. And then we introduced the concept of conditional distributions, where we are talking about the distribution of one variable x conditioned on the other variable y. So, the distinguishing features among these are that in bivariate joint probability mass function and probability density functions, we are talking about the simultaneous behavior of two random variables x and y. And in the case of marginal distribution, we are talking about the distribution of one variable irrespective of the other variable. And in the case of conditional distributions, we are talking about the distribution of one variable x conditioned on the other variable taking on specific values. And we also introduced the concept where the conditions placed on the variable y may be such that y belongs to a certain region, in which case we integrate over that region both the joint probability density function as well as the marginal density function. Now, today we will introduce the important concept of independence of two random variables, and then we will go on to see how we derive the probability distributions for functions of random variables. So, independent random variables, intuitively x and y are independent when the outcome of one of the random variables does not at all influence the outcome of the other random variable. So, we say the two random variables are independent if the distribution of one random variable does not in any way influence the distribution of the other random variable. Now, in many situations, independence is a very useful assumption, especially in hydrologic analysis, but you must not forget that there must be a sound physical basis for this assumption. For example, if physically the two are dependent on each other, the two variables are dependent on each other, and although stochastically you may show that the two variables turn out to be independent based on the data that you have collected and based on the distributions that you fit and so on, but there must be a sound physical basis for the assumption, and only then you should proceed with the with checking of independence of the two random variables. For example, we will take the example where we are talking about inflow to the reservoir, and there is a command area where there is a rainfall that is occurring, and you are interested in the two random variables inflow and the rainfall in the command area. Note that the inflow here in the catchment area of the reservoir is generated by the rainfall in the catchment area, the precipitation in the catchment area, and the rainfall in the command area, if the command area is far removed from the catchment area, may be assumed independent of the inflow that comes to the reservoir here. Now, if however, the rainfall here and the rainfall here are governed by the same processes and they are in the same hydrologic region, then we cannot assume the rainfall and the inflow here as independent. So, there must be a case for you to consider the inflow here and the rainfall here as two independent random variables based on whether or not they belong to different hydrologic regimes, and only then you will be able to take them as independent variables. You take another example where in the class in the lecture number 1 we introduced this problem, where we are interested in the water quality of a stream which is primarily governed by the stream flows and the effluent load, that is the pollutant load that comes at various locations. So, the pollutant load and stream flow may be treated as independent variables, because pollutant load is essentially from anthropogenic activities, although it may be a random variable, and the stream flow is essentially a natural process. So, the pollutant load, which is one of the random variables x, and the stream flow, which is other random variable y, may be treated as independent variables. However, stream flow and water quality indicator, let us say we are interested in the dissolved oxygen at a particular location here. Now, the water quality indicator at this point cannot be treated as independent of the stream flow, because it is directly influenced by the stream flow. So, this is how first we need to make a case for whether the two random variables can be assumed to be independent of each other. Once you have a physical basis on which you may make the assumption that yes, the two random variables can be assumed to be independent, then we go on to examine whether stochastically we can treat them as independent or not. Now, when we say two random variables are independent, what does this mean? This means that the distribution of one of the random variables, let us say x, is in no way influenced by the distribution of the other random variable. So, if you look at the conditional distributions, then conditional densities, let us say g of x given y, conditional density of x conditioned on y taking on a certain value y, will be the same as the marginal density of x, because the density of x is not influenced at all by the density by the conditions placed on y if the two random variables are independent. And therefore, we can write the conditional density as equal to the marginal density itself. And from the definition of the conditional density, recall that g of x given y is given by the joint density f of x given y by the marginal density h of y for h of y strictly positive values. Now, because the two random variables are independent, g of x given y will be the same as g of x, and therefore, we write g of x is equal to f of x comma y, which is a joint density function, divided by the marginal density of y, and from this we write f of x comma y will be equal to g of x into h of y. Now, this is both the necessary as well as sufficient condition for the two random variables to be independent. So, we state more formally that the two random variables x and y are stochastically independent if and only if the joint density f of x comma y is given by the product of the marginal densities g of x and h of y. Now, in the case of discrete random variables, the two random variables are independent if and only if the probability x I comma y j, which is a joint probability mass function, is equal to probability of x I into probability of y j for all I and j, which is stating in words the joint probability mass function must be equal to the product of the marginal probability mass function p of x I into p of y j, the product of the two marginal probability mass functions. Let us see an example. Let us say f of x y, that is a joint density function, is given by x plus y for these limits, x varying between 0 and 1 and y varying between 0 and 1. Now, for independence of x and y, we have seen that the condition that needs to be satisfied is f of x y must be equal to g of x into h of y. So, let us first determine g of x. recall that the marginal density G of x is integral of the joint density over y with respect to y. So, when we integrate this, these are the limits for y, and then when we integrate this, you get x plus 1 by 2 as the marginal density of x. Similarly, marginal density of y is h of y. You integrate over x, the joint density function, and you will get y plus 1 by 2. This is valid over the region 0 to 1, x varying between 0 to 1, 0 and 1, and y varying between 0 and 1 for h of y. Now, your f of x y was x plus y, and you got a g of x is equal to x plus 1 by 2, and h of y is equal to y plus 1 by 2. Obviously, this means that f of x y is not equal to g of x into h of y, and therefore, x and y are not stochastically independent. So, to summarize then, first you must have a physical basis to at least suspect that the two random variables can be taken as stochastically independent, can be taken as independent, and then you examine for the stochastic independence by checking if the joint density function f of x comma y is in fact equal to the marginal density product of the marginal densities g of x and h of y. Look at this example. F of x y is equal to e to the power minus x plus y for x and y both positive values. Now, we will check again the condition f of x y is equal to g of x into h of y. So, first you obtain g of x, again integrate the joint density over y 0 to infinity. So, from here you get g of x is equal to e to the power minus x and x greater than 0. Similarly, h of y, you for getting h of y, you integrate the joint density over x with respect to x. So, you will get h of y is equal to e to the power minus y for positive values of y. So, you get g of x into h of y is equal to e to the power minus x into e to the power minus y, which is e to the power minus x plus y, and therefore, f of x comma y is equal to g of x into h of y, and therefore, x and y are stochastically independent. So, the independence assumption always implies that the joint density of the two random variables f of x comma y is equal to the product of the marginal densities f of x g of x into h of y. I am sorry. So, f of x comma y must be equal to g of x into h of y. Now, we will go on to determining the distributions of functions of random variables. Now, these situations arise quite often in hydrology, where we are interested in getting the distributions of functions of random variables. Let us say there is a stream here and there is another stream here. The stream flow here is denoted by the random variable x, and the stream flow here is denoted by the random variable y. And we may be interested in the distribution of x plus y, which is the combined stream flow that is coming downstream of this location. So, if you know the density of x and the density of y, how do we determine the density of x plus y? That is a question here. Similarly, you look at another example where there is a rainfall occurring in the catchment area, and then there is a associated stream flow here. Now, we may have a functional relationship between the stream flow at this point and the rainfall in the catchment area. Let us say we express this stream flow y as a function of x. Let us say y is equal to x square minus 4x plus 1 or some such function. And we may have the density function, or we may have estimated the probability densities of the rainfall in the catchment area, and we would be interested in getting the probability densities of the stream flow at this location. So, such situations lead to the derived densities for the functions of random variables. We will see how these can be obtained. So, if you have x as a discrete random variable, which means that x can take on only finite number of values or countably infinite number of values, and you define a function y is equal to h of x. So, because x takes only discrete values, y also takes on only discrete values, and we know the probability mass function of x. So, in such a situation, what we do is that associated with each of the discrete value of x, you obtain the discrete value of y, and then knowing the probability with which that particular discrete value of x occurs, the corresponding probabilities of y can be directly obtained. Now, it is possible that the same value of y occurs for different discrete values of x, in which case that particular value of y can occur for x is equal to x1, x is equal to x2, and so on, and the associated probabilities need to be added up. So, in the case of discrete random variables, when you have a function of the discrete random variable, the procedure is fairly straightforward. You simply enumerate all the possible values of y for the discrete values of x, and then we obtain the probabilities of all these possible values of y from the probabilities of the corresponding values of x. See, for example, we have the probability mass function p of x is equal to 60 divided by 77 x, and x takes on the values 2, 3, 4 and 5. So, x takes on only the discrete values, and we define a function y is equal to x square minus 7 x plus 5. So, knowing the probability mass function p of x, we are interested in getting the probability mass function of the random variable y. So, what we do is that associated with each of the discrete values that x can take, namely 2, 3, 4 and 5, you enumerate the values that y can take. For example, when x is equal to 2, y will be equal to minus 5, substituting in this expression here. Similarly, x is equal to 3 leads to y is equal to minus 7, x is equal to 4 leads to minus 7, and x is equal to 5 leads to minus 5. So, y can take on only two values, namely minus 5 and minus 7. So, once we define the probability of y is equal to minus 5 and probability of y is equal to minus 7, we would have defined the probability mass function for y. So, let us see what for what values of x does y take on value of minus 5, let us say. Now, y is equal to minus 5 occurs for value of x is equal to 2 and x is equal to 5. So, probability of y is equal to minus 5 will be equal to probability of x is equal to 2 plus probability of x is equal to 5, which turns out to be 6 by 11, as you can see here. Similarly, the value of minus 7, y takes on a value of minus 7 when x takes on a value of 3 or x takes on a value of 4, and therefore, the probability of y is equal to minus 7 turns out to be probability of x is equal to 3 plus probability of x is equal to 4, which will be 5 divided by 11. Note that because it is a probability mass function, the sum of all the probabilities that you thus obtain should be equal to 1, which in this particular case it is. So, in the case of discrete random variables, I repeat that you simply enumerate the possible values of y, which is a function of x, using the functional relationship, knowing the discrete values that the random variable x can take, associated with each of the discrete random variable, discrete value of the random variable x, you enumerate the value that the random variable y can take and then associate probabilities for each of the values that the random variable y can take. Now, we will go to the case of continuous random variables. Let us say you have the random variable x as the continuous random variable and you define a function y is equal to h of x, which is a continuous function of x. And we are interested in getting the PDF of y, which is the marginal PDF g of y. What we do here is, first we obtain the CDF, the cumulative distribution function of y, where from definition g of y is equal to probability of y being less than or equal to y. How do we find this? You know the functional nature y is equal to h of x, and on this we identify in the range space of x, we identify the event corresponding to y less than or equal to y. For example, let us say y is equal to 2x plus 5, some simple linear function we will take, and we are interested in the event y being less than or equal to y. Remember, the small y indicates the value that the y takes, and therefore, we can write this as 2x plus 5 is less than or equal to y, y is a value, and from this we write x is less than or equal to y minus 5 divided by 2. So, the event y being less than or equal to y is now written as x being less than or equal to y minus 5 by 2, and then we can get the probability of y being less than or equal to y as probability of x being less than or equal to y minus 5 by 2, which we can obtain because you know the probability density function of x. So, from the probability density function f of x, we will get probability of y being less than or equal to y. Now, this defines the CDF of y, which is capital G of y. Once we know the CDF of y, you can obtain the PDF of y. How do we do that? We simply differentiate the CDF with respect to y to get the associated PDF. So, we obtain the small g of y, which is the marginal density of y, from the CDF g of y by differentiating with respect to y. Then we have to examine whether this g of y in fact satisfies all the conditions of a PDF, and this must be non-negative, and also the integral over the entire region must be equal to 1. So, we choose the limits of y from the functional relationships and the associated limits of x. We choose those limits of y over which g of y thus obtained is non-negative, and then we examine over that particular range whether the integral of g of y is equal to 1. So, the procedure is simple, that from the range space x, we obtain an equivalent event of probability of y being less than the equivalent event of y being less than or equal to y, and then get the CDF of y, which is capital G of y, differentiate the capital G of y, which is a CDF, to obtain the marginal density small g of y. Once we obtain the marginal density g of y, we will fix the limits of y over which this g of y is non-negative, and then over those limits we will examine whether the integral minus infinity to plus infinity g of y dy is in fact equal to 1. Let us take an example. Let us say f of x is equal to x by 2 over this region, x varying between 0 and 2, and we define a simple function h of x is equal to 4x plus 1, or we define y is equal to 4x plus 1. So, first we get, and we are interested in getting the PDF of y is equal to h of x. So, first we will obtain the CDF of y from the definition g of y is equal to probability of y being less than or equal to y, and what is y? Y is 4x plus 1. So, 4x plus 1 is less than or equal to small y, from which we write probability of this is equal to probability of x being less than or equal to y minus 1 divided by 4. Now, you know the f of x, which is the density function of x, and you are interested in getting the probability of x being less than or equal to y minus 1 by 4, and x varies from 0 to 2. So, we integrate the PDF f of x between 0 and y minus 1 by 4 to obtain the capital G of y. So, we obtain the capital G of y by this procedure as y minus 1 the whole square divided by 64. Now, we differentiate this to obtain the small g of y, which is the marginal density of y. So, marginal density of y is equal to the differential of the CDF with respect to y, and that we obtain as y minus 1 divided by 32. So, for our original variable x takes on values between 0 and 1, and y is equal to 4 x plus 1 is a function. From this we get the limits of y as y varying between 1 and 9. Verify that within this region where y takes on values between 1 and 9, the function g of y is non-negative. If you put y is equal to 1, you get a 0 value. If you put y is equal to 9, you get a non-negative value here, and therefore, this g of y is non-negative over the entire region as obtained here. Then we will also verify that the PDF so obtained g of y, the integral of that with respect to y over this entire region must be equal to 1. So, this we verify, and that is integral of small g of y with respect to y over the region 1 to 9 must be equal to 1, which in this case turns out to be true. So, in the case of continuous random variables, we first obtain the capital G of y, differentiate that to get the small g of y, which is the marginal density of y, and then obtain the limits of y over which the small g of y thus obtained is non-negative, and then we verify that the integral of small g of y over this region that we have identified is in fact equal to 1. Let us take another a small simple example. This is in fact the exponential distribution lambda e to the power minus lambda x, which we will introduce later on. So, we take f of x is equal to 3 e to the power minus 3 x, where x is greater than 0, and we take h of x is equal to e to the power x. This is x is positive here. So, h of x is equal to e to the power x, and we are interested in getting y is equal to h of x, getting the PDF, I am sorry, getting the PDF of y is equal to h of x. So, first, as we did in the previous example, first we obtain the CDF of y by identifying the event y is less than or equal to y, the equivalent event of y is less than or equal to y in the range space of x. So, this we write it as e to the power x, e to the power of x less than or equal to y, and by taking the logs we write this as probability of x being less than or equal to log y. So, g of y then is probability of x being less than or equal to log y, and therefore, you integrate between 0 and log y the f of x that you have here. So, we integrate between 0 and log y the marginal PDF of x to obtain the capital G of y. This is a straightforward integration and putting the limits. So, we obtain capital G of y is equal to 1 minus y to the power minus 3. Now, we differentiate this to obtain the marginal PDF of y. So, when we differentiate this, you get the PDF as 3 y to the power minus 4. Then from the limit that x is positive, you get g of y is equal to 3 y to the power minus 4 in the range between y is equal to 1 and y is equal to infinity. I introduce this example with a purpose, which we will see presently. So, to repeat again, for the continuous variables, we obtain first the CDF of y, which is a function of x, and the PDF of x is known. Once you obtain the CDF of y, you get the PDF of y by differentiating the CDF, identify the limits over which this PDF is non-negative, and then verify that the integral of the PDF over this region that you have just identified is in fact equal to 1. Now, this can be more generalized, as we will presently see, but this slide shows that the PDF that we obtained 3 y to the power minus 4 is, it satisfies the condition that over the region that you have identified 1 to infinity, the integral must be equal to 1. Now, we will go to some generalization. In the case of monotonic functions, the examples that we just did and the procedure that we just introduced can be generalized, and we can write this in a quite an elegant fashion. First, we will see what are the monotonic functions. We say u x is a monotonically increasing function of x if as x increases, u of x increases. For example, you take a function like this. Now, x 1 and x 2 are here. So, x 2 is greater than x 1. Your function corresponding to x 1 is u x 1. Function value corresponding to x 2 is u x 2. So, u x 2, u of x 2 is greater than u of x 1, as it is in this particular case for all values of x 1 greater than or equal to x 2. In such a case, we call this function as a monotonically increasing function. Similarly, for a monotonically decreasing function, we have the condition that as x increases, the function value decreases. So, we write this as u x 2 less than u x 1 for all x 2 greater than x 1. So, as x increases here, the function value decreases. Now, when we have monotonically increasing or decreasing functions, the procedure for obtaining the PDF of y, which is a monotonically increasing or decreasing function of x, can be simplified, and we write it as follows. Suppose that y is equal to h of x is a strictly monotonic function. It may be either increasing or decreasing function of x, and we know the function the PDF f of x. Then the PDF g of y can be straight away written as equal to f of x into the absolute value of dx by dy, which is the differential of x with respect to y. We are talking about a single random variable and a function of a single random variable. Now, in this case, both x and f of x we express in terms of y. We have the functional relationship here y is equal to h of x, from which we can express x in terms of y, and then that we put it in the PDF f of x, and therefore, we express the PDF f of x also in terms of y. So, we express both x and f of x in terms of y, and then obtain g of y is equal to f of x, which is a function of y, and then absolute value of dx by dy by differentiating x, which was expressed in terms of y with respect to y. We will not go into the proof of this, but we will take this result and then start applying to numerical examples. Let us say you take again the same example that we just explained, f of x is equal to 3 e to the power minus 3 x. As you can see, and then we define a function h of x is equal to e to the power x. Remember here, when we said the monotonically increasing or decreasing function, we are talking about the transformation, the PDF of which you are interested in. So, we must examine for the monotonicity of the function h of x and not f of x. So, y is equal to h of x is the function in which you are interested in. So, y is equal to h of x, which is e to the power of x for x greater than 0, and this is a monotonically increasing function, as you can verify. So, first we will express x in terms of y is equal to e to the power of x, and therefore, x is equal to log y, and then we get dx by dy is equal to 1 over y. Similarly, we have to express f of x also in terms of y is equal to e to the power of x. So, we express f of x as y is equal to e to the power minus 3 x, and then x is log y, from which you get f of x is equal to 3 y to the power minus 3. Because the transformation y is equal to h of x is a monotonically increasing function, we use this expression because it is a monotonic function, whether it is increasing or decreasing, but in this particular case it is increasing function. G of y is equal to f of x absolute value of dx by dy, and dx by dy is 1 by y, and therefore, you get g of y is equal to 3 y to the power minus 4. We obtain the relationship or the range for y as here the range for y will be h of b less than or equal to y less than or equal to h of a if it is a monotonically decreasing function, and h of a less than or equal to y less than or equal to h of b if it is a monotonically increasing function, where h of a and h of b are obtained from these values of a and b. This can be verified here. So, we obtain the limits as y going between 1 and infinity, as was obtained in the example discussed earlier. Okay, the same concept we extend to functions of two dimensional random variables. So, in the case of a continuous bivariate random variable, we have the joint density f of x y, and we are interested in getting the joint density g of u comma v, where u is a continuous one-to-one function of x comma y, and v is another continuous one-to-one function h 2 of x comma y. So, u and v are both functions of x and y. In such a case, the joint density g of u comma v is given by f of x y into the determinant j of u comma v, where j u v is the Jacobian of the transformation. I am sorry, this is the absolute value of Jacobian. The Jacobian u comma v is given by dx by du, dx by dv, and dy by du, and dy by dv, the determinant of that. So, this is the Jacobian of the transformation. We take the absolute value of the Jacobian and then write g of u comma v as equal to f of x comma y into the absolute value of Jacobian u comma v. Again, as we did earlier, x y and f of x y are all expressed in terms of u and v. So, we use the functional transformations here, u is equal to h 1 of x comma y and v is equal to h 2 x comma y, and express x, y and f of x y as they are expressed in terms of u comma v, u and v. So, we will take this example to drive home this point. F of x y, which is a joint density function, is given by 3 by 2 x square plus y square for the range x varying between 0 and 1 and y varying between 0 and 1. We will define the functions u is equal to x plus y and v is equal to y by 2. And we are interested in obtaining the joint density u comma v. Remember here both u and v are functions of x and y, although v does not contain the x term, but in general u and v can be functions of x and y. So, first we will express x and y in terms of u and v. So, from here v is equal to y by 2, we write y is equal to 2 v, and u is equal to x plus y, we write x is equal to u minus 2 v, because this is y is equal to 2 v. So, we write x is equal to u minus 2 v. So, once we express x and y in terms of u and v, we substitute these in the expression f of x y and express f of x y again in terms of u and v. So, we write f of x y in terms of u and v by looking at f of x y is equal to 3 by 2 x square plus y square, and therefore, you express f of x y as 3 by 2 u square minus 4 u v plus 8 v square. Then we get the Jacobian. Now, it is always convenient, in most situations it is convenient to get 1 by j rather than j, as it is in this particular case. So, 1 by j we express it as du by dx, dv by dx, du by dy, dv by dy, and from your expression for u and v you can obtain these differentials. So, 1 by j du by dx turns out to be 1, dv by dx turns out to be 0, because v is equal to y by 2, and du by dy is equal to 1 and dv by dy is equal to half. So, from this the determinant, this is the determinant here, will be equal to 1 by 2, and therefore, j turns out to be 2. So, you have expressed f of x y in terms of u and v, and you have obtained the Jacobian, which is 2, and therefore, you get the joint density of u and v as f of x y into absolute value of the Jacobian, which will be equal to 3 by 2, this is f of x y here, multiplied by 2, which is a Jacobian. Now, we need to fix the limits. These limits are fixed from the fact that u is equal to x plus y and v is equal to y by 2, and x takes on values between 0 and 1 and y takes on values between 0 and 1. So, we fix the limits as y, when y is equal to 0, v will be equal to 0, and when y is equal to 1, v is equal to 1 by 2, and x, when x is equal to 0, u is equal to 2 v. Look at this, u is equal to 2 v, x is equal to 0, so therefore, u is equal to y, which is equal to 2 v, and when x is equal to 1, u will be equal to 1 plus 2 v. So, the limits for these are expressed as v going between 0 and half and u going between 2 v and 1 plus 2 v. Now, once we obtain the joint distribution, we can now obtain the marginal distributions of u and v by integrating over the other variable, as we did in the previous class. Now, in some cases we are given the joint density function, but we are given only one function. Let us say that you have f of x y, which is a joint density function of x and y, and you are interested in the distribution of u is equal to u of x comma y. There is no other v. In such case, we introduce a dummy variable v is equal to v of x comma y, some convenient variable we introduce, convenient function we introduce, and then obtain follow the same procedure as we did just now for the two functions u and v, and obtain the density function, first the joint density function g of u comma v, and then we integrate over v to obtain the density of u. So, when we are given only one function, you can still follow the same procedure as we followed for two functions by artificially introducing another function which is a convenient function, so that it does not introduce any complexities in your computations, and then obtain the joint density function by following the same procedure. Once you obtain the joint density function, you integrate over v and get the marginal density function. For example, you take the same PDF as in the previous example, but instead of having two functions, we are interested in only u is equal to x plus y. Let us say we are interested in the density function of u, where u is equal to x plus y. Then we define a dummy variable as v is equal to y and obtain the joint density function of g of u comma v, and by integrating over the density function y. So far what we studied in this course is, given a random variable, we know how to define the density function, and then we have gone on to bivariate random variables and introduce the concepts of joint density functions, the marginal density function, and the conditional density functions. Then we introduce the concept of independent random variables, which we said the independence is it always ensures that the joint density function f of x comma y is a product of the marginal density functions g of x and h of y. Then we looked at functions of random variables and saw how we define the density functions of random variables. Let us say y is equal to h of x is a function, and we know the PDF of x. We know now how to determine the density function of y. This we extended also to monotonically increasing and decreasing functions, where we generalize the procedure. Then we introduce functions of two random variables, x comma y are the two random variables, x and y are the two random variables, and we are talking about the functions h1 of x comma y and h2 of x comma y. And then we saw how we determine the joint densities of these functions of random variables. Now, with this background, now we will see, we will slightly go to a slightly different topic, in which we will start talking about moments of the distributions. To understand the moments, first we will understand certain basic definitions. We will just go through some basic definitions. You have a random variable x, and it can assume certain values. Now, the collection of all possible values that this random variable can assume is called as a population. So, we will introduce these concepts. First, let us say we are talking about a page being randomly picked up from a thick book consisting of, let us say 1000 pages. So, a page that is randomly picked off is a page in the book is the random variable. What are all the possible values that the random variable can assume? It is the entire set of the pages, let us say 1 to 1000. So, the random variable can take on any value between 1 to 1000. Now, the set comprising of all possible values that the random variable can take is called as a population. Then any subset of that population is called as a sample. Let us say we are talking about pages in a particular chapter. The pages in a particular chapter is a subset of the pages in the entire book. So, the sample indicates a subset of the population. Then we have what is called as a realization. Realization is the actual outcome of the experiments that you have carried out. For example, you have actually randomly drawn certain pages and then you get the series of such values that the random variable has actually taken, and this is called as a realization. An observation is a particular value of the random variable in the realization. So, you have from population, you have a subset of the population which is called as a sample, and we have a realization which is generally used in the time series sense, where the values that the random variable has actually taken is called as a realization, and a particular value in the realization. Let us say you are talking about flow in June month of 1977, which has been observed already. A particular value in the realization is called as the observation. Now, with this we introduce the concepts of movements of a distribution. This is much similar to the movements that we talk about in mechanics. Let us say you have the distribution here f of x, and this is the origin 0 0. So, we define the nth moment about the origin denoted as mu n o as minus infinity to plus infinity, this entire region, x to the power n into f of x dx, where f of x is the PDF. So, we are defining the moments of the probability density functions. So, the moment, the nth moment about the origin is simply minus infinity to plus infinity x to the power n f of x dx. Let us take the first moment. Okay, before that, what happens when n is equal to 0? That means, we are talking about the 0th moment. What happens when x is n is equal to 0? It is minus infinity to plus infinity x to the power 0, which is 1 f of x dx. That will turn out to be 1, because that is the area under the f of x. So, the first moment about the origin when n is equal to 1 is called as the expected value of x. So, we are putting n is equal to 1 here. So, mu 1 0, which is denoted as mu simply, is equal to expected value of x minus infinity to plus infinity x of x into f of x dx. So, we are putting n is equal to 1. So, this is x into f of x dx. We will come to the implications of this later on in subsequent classes, but this is just the expected value of x. Once we know the expected value, let us say we fix the expected value here, then we start taking moments about the expected value, which come in very handy for our analysis. So, first we defined the moments of the distribution about the origin and obtained the expected value. The other moments about the origin are also important and significant, but once we define the expected value of x, we also start taking moments about the expected value itself. So, we define the nth moment about the expected value, which is denoted as mu. We write it as mu n is equal to x minus mu to the power n f of x dx. So, this defines the nth moment about the expected value or about the mean. This expected value is also called as the mean. Now, the expected value has certain interesting properties. First, by definition, expected value of x is equal to x f of x dx. between minus infinity to plus infinity. This is how we obtain the expected value. Now, expected value of C is equal to C into integral of minus infinity to plus infinity f of x dx. That is, instead of expected value of x, we are talking about the expected value of a constant. Minus infinity to plus infinity f of x dx is equal to 1, and therefore, expected value of C turns out to be C itself. So, expected value of a constant is the constant itself, which is quite obvious in the sense that you are given a random variable whose probability density function is known, and you are asking for expected value of 5. So, expected value of 5 will be 5 itself. Then from this it also follows that expected value of C into x is equal to C into expected value of x. We also have to see this particular result, which is interesting, where we are talking about the expected value of a function of x, g of x is equal to minus infinity to plus infinity g of x f of x dx. And from this we again get expected value of a constant into g of x is equal to C into expected value of x. Then we also have expected value of g 1 of x plus or minus g 2 of x must be equal to expected value of g 1 of x plus minus expected value of g 2 of x. Now, these are some interesting results that we will be using in many of the applications subsequently. So, this is the first moment that we are talking about. So, x f of x dx. Similar to the first moments, we can start talking about higher moments, and in general when we go to higher moments, we start talking about moments about the expected value itself. So, we start talking about the first moment, second moment about the expected value, third moment about the expected value, and then we will see what exactly they indicate. So, in the next class we will introduce higher moments and solve some examples, and we also introduce the population moments and their associated sample estimates, because we will have always a sample which is a subset of the population with us, and based on these samples we need to make decisions on the population. So, in the next class we will introduce higher moments about the expected value, and then we go on to provide the sample estimates for these moments. Then we will also take examples of certain continuous probability density functions that are commonly used in hydrology. So, thank you for your attention. We will meet again.